Alrighty, it's Horner again, and here we go. We're going to take a look at Energy F2. This one has a new toy car. It has mass M. It rolls on a nearly frictionless bearings, and so those things are super important. Let's highlight some of those things. So nearly frictionless bearings, and it is a spring-loaded launcher, so we do have a spring we have to worry about. There's our mass. An apparatus which is not shown within the launcher allows the person to compress the spring and then release it. So this is kind of like the carts that we use in class. The student's given the toy and asked to make a hypothesis about the relationship between the spring's compression, so spring's compression, and the subsequent motion of the car. So spring compression, you know that that's going to be X in the equation. F is equal to kx, or if you're doing energy of the spring is equal to 1/2 kx squared. So obviously we're going to need to know something about the k value here. The student hypothesizes that if the cart is launched horizontally, there's another important part, the launch speed of the car is directly proportional to the compression distance of the spring. So what they're saying then is V would be proportional to the compression distance of the spring. So if you plotted those two things, you would get a straight line that looks like that. Write an equation that relates V and X. The equation will necessarily contain some constant quantities. Use the equation to evaluate the student's hypothesis. So at this point, we would need to say, we know that the potential energy of the spring, which is this, should be equal to the kinetic energy of the cart afterwards, which is 1/2 mv squared, and that half does not look like a half. There it does. Now we are set, and we can say 1/2 kx squared is equal to 1/2 mv squared. So we have an equation, alrighty, but it says use the equation to evaluate the student's hypothesis. That means that you need to write something. And if you look here, you'll see that this is x squared and v squared. This is not. So somewhere you need to say that the hypothesis is correct because they are raised to the same power. So if you plot v squared versus x squared, you should get a straight line. So you need to say something about that student's hypothesis is correct because v squared is going to be proportional to x squared due to this equation. You can't just write this and draw lines. You need to use words, so make sure you use words when you answer this. And I would think even about the PEE format for this part. For the next part, it wants you to outline a procedure. Let's do this. This part was worth 2 points. So as long as you have the equation and then you talk about it correctly, that would be good. If you drew a graph, that would be helpful too, probably for the person grading it. But let's go on to the next one. This is 3 points for this procedure. Obviously, there's not enough room here, and you need to draw and label. So you would need more room here, but we can go through and do this. We have to find, one of the things that you need to make sure you do is you need to find the stretch. S-T-R-E-T-C-H. That would involve a ruler of some sort, and then you need to tell how you would measure that stretch. So that would be really important. The next thing that you need to do, you need to figure out how to find the distance, okay, and how to measure the time. And then that way you can find the speed of the cart. So you could say that you're going to use a motion detector. But if you do that, you need to say that it measures distance and time and does not measure speed. Then you have to say that speed is equal to distance over time, and that would be a lot better. You'd have to set up some sort of diagram, but one of the other important things, so here you need a diagram of what you're going to do, and on top of that, you need to make sure that you say you're going to do 3 trials for this experiment, okay? 3 trials for each stretch. And by each stretch, what I mean is you're going to stretch it just a little bit the first time, and a little bit more the second time, and a little bit more. So your stretch needs to increase, and then we should see a corresponding increase in this. If you look at the key that we have, you'll see that it talks about that. And when we say stretch here, we also could mean compression, and that's really what's going on is we're measuring the compression of that spring. We did this lab, if you remember. We had but we didn't do it vertically. We didn't do it horizontally. We did it vertically, and you took a cart, had a spring on it, and you pushed the cart back, and then you went to see how high it went. So we did a little bit different. The next part that you need to do talks about going through the analysis. And so when you do the analysis, you need to make sure that you get all three of the points for that analysis piece. So oops, this is new, so I'm going to move this down a little bit. How would the measurements be used to evaluate the hypothesis? So the first thing you need to do is you need to explain how you're going to find the speed. So first point, oops, sorry, like I said, new pad here. First point is how to find V, and really you're just going to take your D over T, and you're going to do that for the launch speed. So we want this for the launch, L-A-U-N-C, speed of the cart. So that would be really good. Number two, you need to have some sort of representation for spring compression and launch speed. So you need to say you're going to make a graph, and you'd have to say this and then draw it. But this would be a graph of velocity and position. You could also do a table, or you could do a table. Either way, but I think this is going to be better. And then you're going to show how you will check to see if it's directly proportional. So when you graph it, if you say you take all the data in a table and then you graph it, it should give you a linear relationship. And so that's going to be important too. So number two is somewhere you're doing this table or the graph. Number three, you're saying how that should be linear. Okay. For the next part, it says the student glues a piece of felt to the top of the car and then orients the car upside down within the launcher so the car is launched and slides, okay, to rest due to the felt and effects of constant friction. The student hypothesizes that the sliding distance is directly proportional to the compression distance. So here we're going to put distance that it slides, and here we're going to put compression distance. So you can do that, and they're saying that it's going to look like this. They want you to write an equation. So your equation here could be in three forms. We are looking at, we know that on one side we've got to have the energy of the spring, and the other one is the change in the energy, or better yet, we're going to say that's the work done by friction. So work done by friction. And so I'll write that, work done by friction. In order to have the proper equation, you should have 1/2 kx squared is equal to, and now we have the force of friction times some sort of distance. If you wanted to make this better, you could do 1/2 kx squared, and you could say that this is mu, which is the coefficient, times normal force times the distance. And then if you really wanted to be special, you could say 1/2 kx squared is equal to mu times, oh, my mu disappeared, mu mg for n, because it's on a flat surface. So remember, if it's on a flat surface, straight down would be mg, straight up would be n, and those are equal in this case. And then we would have our distance. So best equation to have would be the one that's fully fleshed out, but the other two would also work. So either of those three would be fine. Now that you've done that, you need to say, no, it is not going to work, because you'll see that compression is proportional to, or should be proportional to, the distance. So those are the 2 points that you would get for letter I. Let's go ahead and check out letter I. And in I, this student is performing the lab, and they get the data that you see there. And they want to know, do the data support the student's hypothesis? The best answer here should be no. Yes, you could say, if you wanted to, you could say yes, but then all you can say here is that the compression distance increases the sliding distance. But your better answer here is no. because for each, well, if you look at the difference here, this is going to be 0.01, this is 0.01, this is 0.01, so it's going up pretty constantly, but you'll see that this goes from 0.05 to 0.2. So we're going up by a factor of 4 there. Here we went up by a factor of about a little over 2. Here another one a little over 2. Here this one went up by a different factor. So you could actually plot that and kind of see it. So you need to say no. The graph of, and the reasoning is the graph of your sliding distance versus compression distance is not going to give you a straight line. Instead, it will give you some sort of funky curve here. And then you need to just show that when you divide these out, it will not give you a straight line. So 0.051 divided by 0.01 will give you some sort of value. We will call that value A, but that will not be equal to B, which will not be equal to C. So if you're just dividing these, that's kind of the same thing as looking to see what the slope might be. And if the slope is the same, okay, then each one of these numbers should be the same, but they're not going to be as you go through. And that is worth 2 points. So that is the end of that question. Hope you enjoyed it.